Welcome to Vision Plus and welcome back to this senior for mathematics and complex numbers. We are now on example 2 under polar form of the complex number. Example 2 says that we need to find the polar form of the following. A, we have 3 minus 4i. To make your work easy, just say let z be the complex number 3 minus 4i. In the polar form, we need the magnitude of the complex number and the argument of the complex number. So the magnitude r becomes the square root of x, which is 3 squared, plus y, which is negative 4 squared. This gives us the square root of 25. There's a calculator, and then this gives us the 5 units. That is the magnitude of the complex number we are calling r. And then to find the argument of the complex number, we need to represent the complex number on the Argand diagram. In the Argand diagram, this is the real axis of the complex number we have called z. This is the imaginary axis of the complex number z. So we need to indicate 4, negative 4 and 3. So on the real axis we have 3, which is somewhere here. This is the origin. Then on the imaginary axis we have 4, which is there, and the corresponding negative 4 is there. Then we have 3 and negative 4. Real axis is 3, imaginary axis is negative 4. So they are going to meet somewhere here. This is where they're meeting. Let me draw a straight line from the origin up to where they meet, put an arrow, and say this is my complex number z. Now the argument is the angle from here up to where the complex number is, simply. Or somebody could just get the principal argument on the sides. But either way, we have correct answers. So what can I do? Let me just go with our usual method, 90 degrees, so that we are consistent with this 90 degrees. Now we are left with finding this small angle, so that we add it to 90 and 90 and 90. So from here up to here is 3 units. From here up there is 4 units. Please extract the triangle so that you can easily visualize it. Let me call this small angle beta. So to me, I'm going straight. I will just say tan of angle beta is going to be the same as opposite to the angle which is 3 out of adjacent to the angle which is 4. So the angle beta now becomes the tan inverse of 3 out of 4, which is around 36.87. 3 divided by 4, tan inverse, yes, 36.87 degrees. That is just the beta, which is the small angle. Now to get the argument, we need to add 90 plus 90 plus 90, that is 270 degrees, plus this small angle that we have obtained, 36.87 degrees. This gives us, it's like 310 plus 270 degrees, 306, 306.87 degrees. This is our argument. Even if it is not the principal argument, it is also correct. Therefore, because we know that from the complex number that is given by r into cosine of angle theta plus I sine of that same angle. That means we substitute what is the value of r? It's 5 units here. So we can say 5 into cos of the angle 306.87 degrees plus I sine of 306.87 degrees. Or you can use the other format, but choose one. It is given by r comma theta. This gives us here 5, and then the angle is 306.87 degrees. So this is the solution. What if we had obtained this angle instead as the principal angle? The principal angle, this is just alternative. Principal argument, it just becomes 360 minus that angle that we have obtained. That gives us now the principal argument of z is negative 53 0.13 degrees. Now, what if we had used it instead? Now, that would mean that our polar form becomes 5 into cos of negative. This one needs us now to keep curly bracket. You can use square bracket here. Then this is negative 53.13 degrees plus I sine of negative 53.13 degrees. The cosine of this angle is the same as the cosine of that angle. The sine of this angle is the same as the sine of that angle. But always use the one that you are okay with. But the two answers are the same. So this is the solution to part A. Let us go to part B. So going to part B. Part B says that we have 5 plus 5 root 3i. So we say let the complex number z be 5 plus 5 root 3i. And in the polar form, we need to find the magnitude of the complex number r. So the magnitude complex number r becomes the square root of x, for which x is 5 squared, plus the square root of y, no, plus the square of y, not the square root, 5 root of 3, and then we square it. And then you press the calculator. What is 5 squared? Is 25. 25 plus what is 5 root 3 squared? It is, you open the bracket, you say 5 root 3 close bracket squared. It is 75. 75. Because it is the same as 25 times 3. 25 times 3. Yes. Plus 25, that is 100. What is the square root of 100? It is 10 units. That is the value of r. Now let us go on to find the argument of the complex number so that we can write the polar form. So we come and represent it on the Argand diagram. This is the imaginary part of z. That is the real part of z. This is the origin of the complex number. Now we have 5 on the real axis. Let me put it somewhere here, 5. And here we have negative 5. And then here we have 5 root 3. That is slightly bigger. So let me put here 5 root of 3. 5 root of 3. But we are not drawing to scale. We are not drawing to scale. So the distances, there is no punishment for how you locate them. Both are positive. That means they are coming to meet up here in the first quadrant, which has positive values. So they are meeting somewhere here. Then you draw a straight line from the origin up to that point of intersection. Then you say this is my complex number z. Where is the argument? Now the argument is this angle that we make with the positive x-axis. How do we get this argument? This angle here, this is the argument. So from here up here is 5 root of 3. Then from here up to here is the distance 5 units. You can extract the triangle so that your work is easier. And now I'm going to go straight away. I'm going to say this angle is going to be the argument straight away. Why? Because we don't have other small angles that we need to add to the non-standard angles. So I'm just going to say now tan of theta equals to opposite to the angle is 5 root of 3 out of adjacent is 5. That means here tan theta equals to root of 3. So theta now becomes tan inverse of root 3, which as it was 60 in our previous examples. Tan inverse of root 3, 60 degrees. So 60 degrees. Now this 60 degrees is the argument, and it falls in that range that we looked at. So it is the principal argument, but don't stress yourself. As long as it is the argument, use it. Therefore, we know that the polar form of any complex number is given by r open bracket cosine of theta plus I sine of theta. This means that we need to substitute for r, which is the magnitude of the complex number 10, into cosine of 60 degrees plus I sine of 60 degrees. And that is the answer. Or somebody could use the other form, that the polar form is given by r theta, whereby r is 10 minutes and the theta is 60 degrees. This one is also correct. So this is the solution. And then going to part C. Part C says that we need to find the polar form of negative 5i. So we shall just say let the complex number z be the same as negative 5i. What do we need to find? We need to find the magnitude of the complex number r and then the argument of the complex number so that we can find the polar form. So the magnitude r is given by the square root of x. But if you look here, there is no real part. That means the real part is 0. 0 squared plus, what is the y, which is the coefficient of the imaginary part? It is negative 5. Then we square it. This gives us here square root of 25. Then we are getting 5 units as our value r. Most of them in this case are giving us 5 units, but just use the answer we have obtained. Then going to the next part, we need to find the argument of this complex number. That means we need to represent it on the Argand diagram. So this is the real part of this complex number, real axis. This is the imaginary axis of z. This is the origin. Now we need to indicate negative 5. Remember, the real part is 0. So let me mark the imaginary part here 5, then the corresponding negative 5 there. Just to make it look nice, you can also mark that axis in that format. But remember, on the imaginary axis, we need negative 5, which is here. On the real axis, we need 0, which is here. So the two complex numbers, or the two values, are going to meet here. The two parts. So we draw straight line with an arrow on it, like that. What is the argument now? The argument becomes the angle measured from here up to where the complex number is. And we know that this side is 90 degrees, 90 degrees, 90 degrees. They form together the argument. So here we are not forming any triangle because these are standard angles. So what can we do? We just need to add. Now the argument becomes 90 plus 90 and plus 90. This gives us here 270 degrees. This is the argument. So we just say from the general form that the polar form is given by r into cosine of the angle theta plus I sine of the angle theta. Let's substitute for r. R is 5 units. So here we shall have here 5 units into cosine of the angle, which is 270 degrees plus I sine of the same angle 270 degrees. Or you can have it in the other format that says that the polar form is given by r, theta, which is the argument. This gives us 5 units, which is r, and then the angle is 270 degrees. If you look here, we have used the argument, which is not the principal argument.